Newton's grasp of gravity was sufficient to enable us to travel from the Earth to the Moon. If you ever feel disoriented in the relentless march of time, questioning whether our comprehension of it is merely the surface of a deeper mystery, remember, his discovery is not just a hypothesis. It could open the door to the secrets of the universe, unveiling a cosmos more complex and awe-inspiring than we ever imagined. How does Brian Cox's novel theory challenge our traditional conceptions of time? And what could it mean for how we perceive reality? Come along with us on a fascinating journey through the fabric of time as we explore Brian Cox's recently revealed, groundbreaking hypothesis on the nature of time in the vast cosmos surrounding us. Riddles are waiting to be solved, many of which revolve around strange aspects of time and gravity, both integral facets of our existence. They depict a world where time behaves oddly. It can either slow down or accelerate. Moreover, the force that keeps us grounded may not be what we believe it to be. This is the area of Albert Einstein's theories of relativity, where our perception of gravity and time takes a bizarre turn. According to Einstein, a name familiar to all, he presented us with a fresh perspective on the universe through his relativity theories. His work laid the groundwork for understanding how time behaves under various circumstances, especially when moving at incredibly high speeds. It all began in the early 20th century when Einstein introduced two revolutionary concepts: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our conception of time. To put it another way, it asserts that the physical laws remain consistent for all observers who are not accelerating, despite their movement. This theory explains relativistic outcomes, such as the well-known idea that time can stretch or slow down under certain circumstances. One captivating thought experiment often used to explain time dilation is the light clock. Imagine being inside a spacecraft moving at an extremely fast speed, near the speed of light. Inside the spacecraft, a light beam bounces between two mirrors, perpendicular to the direction of travel. According to the laws of physics, the speed of light remains constant for everyone who watches. Therefore, the light beam must appear to follow a longer diagonal path to an outside observer. Since the path is longer for the outside observer, it seems to take more time for the light to complete its journey. This perceived time difference between the two observers is what Einstein referred to as time dilation. Time moves slower for the observer in motion relative to the stationary one. In this case, time behaves differently depending on velocity. Understanding how objects change when they move quickly, also known as relativistic effects, is more than just a theoretical concept. Scientists use large machines such as particle accelerators like the Large Hadron Collider to propel particles to near-light speeds. When objects move at such high speeds, we must consider time in a special way to make precise predictions and measurements. Albert Einstein introduced the special theory of relativity in 1905, revolutionizing our understanding of the universe, particularly regarding time and motion. This theory challenges what we might intuitively believe. It states that the principles of physics are the same for everyone, even if they are not at rest. This is different from everyday life, where we might assume that if we already have something moving and add more speed, it simply gets faster. However, Einstein's theory states that there is a maximum velocity that nothing can exceed: the speed of light. In this framework, events that seem simultaneous for us might not appear the same to someone approaching the speed of light. Another concept that arises from this special way of thinking is length contraction. This indicates that an object appears shorter in the direction it is moving when viewed from a stationary position. In addition to the well-known equation E equals mc squared, which shows that energy and mass are interchangeable, this is crucial for comprehending how small particles behave at high speeds. It also helps explain processes like nuclear fission. In the real world, special relativity isn't just an abstract idea. It plays a role in everyday technologies like GPS. When GPS satellites send signals to your device, they are in motion. Due to this movement, time behaves slightly differently for them. If our GPS systems didn't account for time dilation, location calculations would be significantly inaccurate. Thus, special relativity teaches us that time is not uniform across all places and circumstances. It depends on how things are moving. This notion challenges our typical understanding of time and space, suggesting that our conventional view of the universe is a bit flawed. According to the special theory of relativity, time isn't constant. It is influenced by motion. Some fundamental ideas, such as the constancy of the speed of light and the relationship between energy and mass, have been confirmed by numerous experiments. However, there's more. Enter Albert Einstein's general theory of relativity, published in 1915. This theory delves deeper into the connection between gravity and the structure of the universe. It reshapes the traditional notion of gravity as merely a force. Instead of simply attracting things, it proposes that space and time are warped or curved. This suggests that gravity is not an invisible force but rather a natural consequence of the way space-time bends. According to Brian Cox's interpretation, general relativity requires us to think of the universe as an entity with 4 dimensions, 3 spatial dimensions and 1 temporal dimension. Within this model, massive objects like stars, planets, and even humans influence the curvature of space and time around them. This curvature is what we perceive as gravity. Imagine space-time as a vast elastic sheet. When something massive like Earth is placed on it, it causes a depression in the sheet. If you place something smaller like a ball near Earth, it will roll toward this depression. This is similar to how objects behave due to gravity, not because of some invisible force, but because of the way space-time bends. General relativity provides a robust explanation for the movement of objects in our solar system, such as the orbits of planets around the Sun. It can precisely predict the paths these planets follow. For example, Earth traces an elliptical orbit around the Sun, which aligns with Einstein's curved spacetime model. This contrasts with the old idea of gravity as a simple pulling force, which struggled to explain planetary motion. The new theory, which describes space and time as a flexible fabric, better aligns with what we observe. A landmark event that demonstrated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed close to the Sun. According to the theory, the Sun's mass would cause starlight to curve slightly. Observations during the eclipse confirmed Einstein's predictions, proving the theory's validity. Just as motion can alter our perception of time according to special relativity, gravity also affects time in general relativity. Areas where gravity is particularly strong and intense cause time to flow more slowly compared to areas with weaker gravity. So, if you were standing near a massive object like a black hole, your clock would tick more slowly than one placed farther away. General relativity's concept of enormous mass introduces the idea of black holes, which are regions where gravity is so powerful that the only way out is through the event horizon. A black hole is surrounded by a boundary known as the event horizon, which marks a point of no return. Once an object crosses this boundary, it is drawn into the black hole without any possibility of escape. Einstein's theory of general relativity has profound implications for the structure of the universe. Initially, he added the term cosmological constant to his equations because he believed the universe was static. However, upon discovering that the universe is expanding, he referred to this as a great mistake. The idea of an expanding universe based on general relativity is fundamental to the Big Bang theory, which describes the origin of the universe. Another key concept of general relativity is gravitational waves. These are ripples in the fabric of space and time caused by extremely massive objects moving rapidly, such as when black holes merge or when neutron stars collide. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing further proof of Einstein's theory. Over time, scientists have conducted numerous tests to validate general relativity, and each time the theory has been proven correct, whether by observing the motion of planets, the bending of light, or the detection of gravitational waves. General relativity remains a robust and reliable framework. While claiming that gravity is a myth may sound startling, especially since we experience it every day, in the field of physics, it is normal to challenge and reconsider previously accepted theories. Scientists like Brian Cox regularly question prevailing wisdom, and in the study of gravity, there are opposing points of view. One theory that challenges conventional gravity is modified Newtonian dynamics, MOND, which suggests that gravity acts differently at low speeds, particularly in galaxies, without the need to invoke dark matter. Instead of positing invisible matter, MOND proposes that gravity strengthens at slow speeds. Also involved in the discussion of gravity are the enigmatic concepts of dark matter and dark energy, introduced to explain certain cosmic phenomena. Critics argue that these ideas may be unnecessary and that alternative explanations can account for what we observe. Some scientists oppose these new directions and explore possibilities such as unknown forces or particles that might alter or enhance our understanding of gravity. It is important to recognize that in science, new ideas are not dismissed outright. Instead, they undergo rigorous testing to determine whether they hold up. For instance, Einstein's concept of time as part of a four-dimensional continuum, where time travel may be limited by the speed of light, has been creatively explored alongside concepts like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that time travel into the past is unlikely from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can explain gravity in a manner that aligns with our current understanding. While many ideas have been considered, none have convincingly replaced the well-established laws of gravity. Questioning and rethinking established theories is an essential part of scientific progress, fostering further research and a deeper understanding of the universe. In the field of gravity theories, general relativity remains the most significant and successful one. Despite competing ideas and challenges, it consistently performs well in experiments and explains various phenomena such as planetary motion and the bending of light around massive objects. General relativity endures because it is simple and accommodates a wide array of phenomena. As previously discussed, Einstein's special theory of relativity suggests that time can behave differently depending on your speed. Now, let's explore how this idea affects real-life scenarios, particularly in space exploration. Space exploration is thrilling but difficult because space is vast. According to Einstein's theory, the speed of light is the fastest possible speed, making interstellar travel a major challenge. Even with advanced technology, the long travel times required to reach even the closest stars pose a significant obstacle. To understand what happens to time when traveling in space, consider the well-known twin paradox. Imagine one twin remains on Earth while the other embarks on a fast journey to a distant star. When the space-traveling twin returns, they discover that less time has passed for them compared to the twin on Earth. In essence, they have traveled into the future. Time is critical for space travelers because the longer the trip, the more time slows down for them. If astronauts were to visit nearby stars where time dilation is significant, they would age more slowly than people on Earth. While this may seem like science fiction, it is a real effect predicted by relativity. Imagine humans sending a crew to a distant star system. Due to the vast distances involved, the journey could last many years. If they travel quickly, the astronauts aboard the spacecraft would experience time more slowly due to the time dilation effect. However, from Earth's perspective, significantly more time would have passed. Time dilation affects not just living beings but also technology. Computers and communication devices on spacecraft must account for time dilation to function accurately. Space travel at high speeds also brings physical challenges, such as isolation, exposure to cosmic radiation, and the psychological toll of being far from Earth for extended periods. Even in our daily lives, we can observe time dilation effects. The Global Positioning System, GPS, depends on the precise timing of signals from moving satellites. Because these satellites experience time dilation, it is vital to factor in these effects for accurate GPS readings. Neglecting this would lead to substantial errors in navigation. Now let's examine why time only flows in one direction. Time governs our lives, moving from the past to the present and into the future. This one-way passage of time is fundamental to our reality. But why does time have this irreversible nature? To understand this, we turn to the concept of entropy, a measure of disorder or randomness in a system. Entropy, which is tied to the arrow of time, tends to increase as time passes, driving time to move in one direction. The second law of thermodynamics expresses this relationship, stating that entropy in any closed system will always increase or remain constant. In simple terms, entropy naturally tends to rise and never decreases on its own. Observing how things move toward disorder around us helps illustrate the one-way flow of time. Picture a deck of neatly arranged cards. If we shuffle them, they become disordered. This change from order to chaos demonstrates the unidirectional nature of time, as seen in everyday occurrences like melting ice or stirring a cup of coffee.